Hello everyone, I hope you're all healthy and you're all doing well. In today's lecture, we're going to cover section 5.6, the method of substitution. Why are we learning about this section? Remember last time in the previous video, we learned the fundamental theorem of calculus, and the second part of the fundamental theorem of calculus told us that if you want to find a definite integral of a function over an interval, it suffices for you to have an antiderivative for that function over that interval, because in that case, you can evaluate the antiderivative at the endpoints of the interval, and you can just subtract those values, and that will give you the value of the definite integral. Okay, that's good, but how are we going to find antiderivatives? Well, I've listed some antiderivatives, remember last time, of some basic functions, but if you grab a random function that an engineer runs into in practice, that function will most probably be not in those tables, because it's going to be a composition of certain functions with something else, and maybe you're going to take products, you're going to take quotients, and so on. The point is, when you need to integrate, you won't be always able to find your function in those tables, which means that you should learn about techniques which will allow you to reduce whatever you have into cases which you can integrate via looking at those tables. Okay, so we're going to learn about integration techniques in the next couple videos. The most basic one is the substitution method. Okay, so let me talk about substitution method today. The substitution method. Substitution method. The idea behind the substitution method is very simple. It's simply like the whole idea is using the chain rule. How? Recall that if f and g are differentiable functions, let's pretend for a second that they're differentiable everywhere so that I can compose these nicely. Otherwise, I have to say things like pretend that f is differentiable at points which are a range of g and so on. I don't want to say these, so I'm just going to say that everything is differentiable everywhere, which is not the case in practice, but so I'm going to say it like that. Functions. Then, now remember the chain rule. The chain rule tells us that the derivative of f composition g is given by f prime of g of x times derivative of the inside g prime of x. Okay? Thus, we have the following. The integral, the indefinite integral of f prime of g of x times g prime of x dx is f of g of x plus c. Okay? So we have that. Okay, so what? Like, why is this useful? Let's think about this. If we let u be g of x, then we have that okay, so I'm just going to rewrite the whole indefinite integral here. Now, if I think of this g of x as any variable u, this is f of u plus c. Okay, but this is the indefinite integral of f prime of u with respect to u. Okay, indeed, like to understand this, you just try to read this equality from right to left. Pretend that you have f prime of u du, okay? So you're treating u as an independent variable. What is the indefinite integral of f prime of u du? Well, f is an antiderivative for f prime, so it's f prime of u plus c. But if I think of pretend that my u were not an independent variable, but it depends, like it's g of x for some function g, for some differentiable function g, then this would be f of g of x plus c. But this is an independent. This function f composition g as it's an antiderivative for f prime of g of x times g prime of x. Okay, with respect to x. So this suggests that given an indefinite integral of the form f prime of g of x times g prime of x dx, we can turn this integral into the integral of f prime of u du by letting equal g of x, and it may be that the second, the lateral integral is easier to find. Now, the whole thing suggests you to do the following. Like, you have an indefinite integral. Indefinite integral of f prime of g times g prime of f prime of g of x times g prime of x dx, okay? If you call your g prime of g of x u, then this integral will turn into something possibly quite simpler, okay? But how do you know that your integral looks like this? Like f prime of g of x times g prime of x. Like, you don't see why should an arbitrary integral that you run into in practice should look like this? They will not. What you're supposed to do is you're supposed to make them look like this so that you can apply this technique and write them as an indefinite integral, which is presumably simpler. So this whole thing suggests that if when I give you a function to integrate, like you're supposed to find an indefinite integral of a function, I give you a function. If you can find some expression, some function of x, which when you call it g, your integrand looks like f prime of g of x times g prime of x. If you can find such a g, then this whole thing suggests that replace that g with u and that replace g prime of x dx part with d. Okay, so this whole thing suggests that when you see this whole thing suggests doing such a substitution, which is why this is called the substitution method. Okay, so I'm substituting u for g of x and du for g prime of x dx. Okay, now let me show you some examples. In the previous videos, in the last 2 or 3 videos, we focused on theory a lot. I wasn't able to solve many questions because there were simply not many questions to solve. In the following videos and in this one, we're going to be solving more questions than usual, so don't worry. I think I have like 6 or 7 questions in mind to solve. We'll see, depending on our we'll see how many I will solve depending on our pace. So first one, find indefinite integral of e to the power x plus sine x divided by e to the power x minus cosine x dx. Okay. So you can find this function in those antiderivative tables that are in your lecture notes or in your book. So what are you going to do? Now, the substitution method is like when you need to integrate something, you will learn a lot of methods like integration by parts, partial fractions, inverse trig substitutions, and so on, so forth. But the first method that you should always try is the substitution method, because the point of substitution method is to take some seemingly complicated indefinite integral and turn it to a simple indefinite, turn it to a simpler indefinite integral. How? Within your integrand, you should find some function of x, some expression of x, which you're going to call your u. So that will be your g of x here. So that the derivative of that with respect to x is also seen within the integrand, which is this part. If you can find such a u, then what like our observations above tells us that, okay, then just replace that thing with u, like instead of that just write u, and instead of this g prime x dx part just write du. Okay, and then your integral will probably get simpler. Now I ask myself this question when I look at this: can I find some function of x in this integrand whose derivative is also seen in this integrand? The answer is, well, let's see. The derivative of e to the power x is e to the power x, so it's up there. The derivative of sine x is cosine x, and the derivative of cosine x is minus sine x. So it is likely that, like, when I call some expression here u, like sine, the numerator or denominator, one of the derivative of u will also be seen in this integrand. Okay, and this is actually the case. So let me solve this. Okay, when people apply substitution method, what they do is this. The procedure that I described over here, they basically write it like that in the solution. Okay, I want to do a substitution. I'm going to call something u, and then this, I'm going to do the substitution and try to get a simpler integral. So what am I going to call u? I'm going to call, okay, the denominator, the derivative of cosine is minus sine, so I have another minus sine, so it's going to be plus sine. Derivative of this will be plus sine of x. Derivative of this guy will be itself. So I see that the derivative of the denominator is the numerator. So why don't I call the denominator u? Okay. And in this case, the derivative of I'm going to take the derivative of the left hand side, which is e to the power x plus sine x. This part times dx will be my du. You see, this is the g prime that I was talking about. Okay, so I'm simply going to write this, and then what this tells me is that, okay, when people write such things, that this means that I'm going to do a substitution, and my u will be e to the power x minus cosine of x, and then e to the power x plus sine x dx will be my du. So this whole top part becomes du, and at the bottom I see I have u. Okay, now I get the indefinite integral of 1 over u with respect to u. And u is here a dummy variable. This is the same thing as the well, okay, no, I'm taking that back. There's something important there. I'm taking that back. U is not as dummy as you think at the moment. So this indefinite, this is the indefinite integral of one of u with respect to u, and I know what that is from the antiderivative tables, some of which we covered last time, and there are tables in your book, so go and read them. I haven't listed all antiderivatives that are listed in your book in the previous lecture, so go and take a look at these, and you'll see that this is ln u plus c. Okay, so I found it. Now, here is one thing that you should not do when you're doing integration. The question is, find the indefinite integral of this function with respect to x, meaning the answer should be a class of functions of x. So whatever my answer will be, that like this is, remember, it's a class of functions which all differ by a constant, but those functions are functions of x. But here, my answer seems to be a function of u. Well, there is no u in the question. U is something that I introduce. So what I should do here is I should not leave it like this, but I should actually replace u by whatever it is, which is in this case e to the power x minus cosine of x. Okay. And now we are done. You can actually double check this. When you take the derivative of this, you're going to get this expression. This is an antiderivative for this function. And when you add this plus c, you get all possible anti-derivatives. Okay, so that's that. Now let me talk about why I told you that u is not a like, we call this a dummy variable for the integral, right? Like in the definite integral, we did that. Over here, it's not a dummy variable. It actually plays a role. Here's the thing. Over here, you can't simply say that, okay, this is a dummy variable just like it was in definite integral, so I'm going to replace this by x. If you replace this by x, then you get this, and this is not what you want. Okay, this is why I like, for a second I said that use a number variable, then I realized that like saying that can actually lead to something dangerous that you should not be doing, so I took that back. What I initially want to mean was that, well, instead of you can use any variable you want, as long as it's not x, or as long as it's not any variable which is previously used. Okay, anyway, so that's that. Now let me find some indefinite integrals here. Remember, we found the if you look at the table of indefinite integrals that I gave you last time, you have we've listed indefinite integrals of a sine and cosine and a secant squared and secant tangent. But what's the indefinite integral of tangent? What's an antiderivative for tangent? Well, let me find this very quickly over here. Now, tangent is sine over cosine. Okay? Sine over cosine. And I ask myself the following question. Can I find some function of x in this integrand? Can I find some expression of x, which, if I call u, will give me a u prime in the integrand? Like, can I find some expression of x whose derivative is also seen in this integrand? The answer is yes. The derivative of sine is cosine, derivative of cosine is minus sine. So I can use both. Which one am I going to use? Now, I'm going to do the correct substitution, and then we'll show you on this question. Well, okay, never mind. Maybe I should show it here. I'm going to do the correct substitution first, then I'm going to show you if you what happens if you use the wrong substitution. So I'm going to call cosine of x u. Okay, then minus sine of x dx will be your du. Okay, and then this integral, this indefinite integral, will turn into sine of x dx is, well, you have that minus sine of x dx is du, so sine of x dx is minus du, and well, let me write minus 1 times du, divided by cosine x is u, so you have that. And this is minus ln of absolute value of u plus c, which is minus ln of a cosine of x plus c. Okay. Now, you could object to this and say that, okay, derivative of sine is cosine, and I see that in the integrand as well. Why don't I try to use that? Because it's not going to work. You see, if you try to use this substitution, sine of x equals u, then cosine of x dx is du, you don't, like, you see the derivative of sine in the integrand, but it's in the denominator. So you don't see you don't have cosine of x dx here, you have dx over cosine x, okay? So when I said that, like, you look for an expression whose derivative is also seen in the integrand, it should be seen as a factor of the integrand, like it should be blah blah times your derivative dx, okay? So you're looking for this expression. Even though you see the derivative of sine in this integrand, it's in the denominator, so it's not going to work. It's not going to help. So if you try to do this substitution, it's not going to be useful. Okay. So this is all the derivative of tangent, and you can easily get a derivative of cotangent as follows. This is cosine over sine. So I'm going to do the exact same trick. I'm going to call what I have in the denominator u, so cosine x dx will be my du, okay? And then this will turn into cosine of x dx is du, so this is du over u, so this is ln absolute value of u plus c, so this is ln absolute value of sine x plus c. Okay. Now, let me also show you the derivative of secant. This one is actually not that easy, which is why I'm doing it. Let me also find a, did I say derivative? Okay, I'm sorry. Let me also find the indefinite integral of a secant. Now, secant is 1 over cosine. So you may ask yourself the following question. Okay, what am I going to call u? I mean, there's only one thing, cosine, but then I don't see minus sine x dx in here. So what am I going to do? Here is a trick, which is used to get the integral of secant. I'm not expecting you to come up with such things off the top of your head. This is like a very smart trick that some smart people discovered. I could have actually checked it out before I started the video, but I can't right now. So what I'm going to do is I'm going to divide and multiply the I'm going to divide and multiply by the same expression, which is going to be secant of x plus tangent of x. So why am I doing this? Now, if you do that, you'll see that what you get is, at the top, at the numerator, you get secant squared plus secant tangent. And at the bottom, you get, well, tangent x plus secant x. And then, at this point, you can do the following substitution. If you call tangent of x plus secant of x u, derivative of tangent is secant squared, and derivative of secant is secant tangent. So what you have at the numerator will be the derivative of this guy. So this is going to be your du, okay? And then this will give you secant squared x plus secant x tangent x dx is my du, so I have du over u, so this is ln absolute value of u plus c, which is ln secant x plus tangent x plus c, okay? So that's that. And with a similar trick, you can also find the okay, yes. With a similar trick, you can also find the I keep saying derivative. I keep saying derivative for some reason, where I mean a indefinite integral. You can by a similar trick, you can also find the indefinite integral of a cosecant as let's see, what is this? This is minus ln absolute value cosecant x plus cotangent of x plus c. Okay, so apply the same trick. Apply the same trick with, instead of multiplying and dividing by secant x plus tangent x, you're going to do the exact same thing with cosecant plus cotangent. Okay, and then you will get that. Okay, that's that. And oh, we did that. Let's see what I want to do next. Okay, good. So we're gonna see more examples. So these are some basic examples where we use the substitution rule. But if you look at these, you'll see that these are all indefinite integrals. Is there a version of the substitution rule for definite integrals? The answer is yes, because we know like definite integrals are evaluated via indefinite integrals by antiderivatives. So like we should be able to write some formulation of the substitution rule for a definite integrals as well, and here it is. Okay, let G be differentiable on a set on an interval. Well, do I want that? No. On a, b, and continuous on a, b, and suppose that f is continuous on the range of G. Okay, then let me use W now. Well, okay, not W, let me use U. Okay, then we have this. So let's first understand the statement, and the proof is like it's two lines. Okay, now what this says is this: pretend that I have a definite integral now, not indefinite integral, and I observe that the integrand in my definite integral looks like this: some function of g of x times g prime of x dx. In this case, what you can do is, just like before, you can call this g of x u and replace g prime of x dx by du, but you have to be careful. This is a definite integral. The upper and lower limits of this definite integral will also change accordingly. Okay, they will change to a g of a and g of b. Okay, now why? Here's the proof. So let f be an anti, well, let a f of x be an antiderivative for little f of x. Then the derivative of this expression is going to be big F prime of g of x times g prime of x, and if big F is an antiderivative of little f, this is going to be f of g of x times g prime of x. I'm going to check something. And so, by the fundamental term of calculus, we have this. How do I compute this definite integral? I find an antiderivative for this, evaluate at the endpoint, subtract blah blah. Well, this is my antiderivative because I just observed that it's an antiderivative. I took its derivative, I got my integrand. So I need to evaluate this from a to b. Okay, so this is f of g of b minus f of g of a, but this is the same thing as f of x, well, f of, let's call this u, evaluated from g of a to g of b. And then this, by fundamental term of calculus, is equal to the definite integral of f of u du from g of a to g of b. Okay, so over here I used FTC, the fundamental term of calculus, again over here. Now then this finishes the proof, and what this term tells you is that you can just apply substitution method for definite integral. You can apply substitution method for definite integrals just like you're applying a substitution method for indefinite integrals, except in a definite integral you have the upper and lower limit, right? Because it's a definite integral. You're like, what's the definition? You're constructing these sums, blah blah. You have to have an interval at the beginning to start with, and that interval, when you apply a substitution, that interval will change. It will change to, you see, if your substitution is u equals g of x, so that du is g prime of x dx, these upper and lower limits of the definite integral change accordingly. So here you had a. Here, instead of that, you're going to plug in a for x. So you're going to get g of a for u. So you're going to write g of a here, and this will turn into g of b. Now, let's see this in action. Example. Find. Let's solve this one. Find this a definite integral. Now, how do I find a definite integral? Ideally, if I were very smart, I would just do everything with Riemann sums. But you know what the problem with that is? Just it will just get too messy. So what do? I need to apply the fundamental term of calculus. So in order to apply that, in order to apply part 2 of the fundamental term of calculus, what do I need to do? I need to find an antiderivative. Okay, so in order to do that, in order to find the indefinite integral of this function, what am I going to do? It's not in the table, so I try the first method that I learned, which is the substitution method. So I'm looking for some expression whose derivative is also seen in this integrand as a factor. Okay, there are not many choices. I can call x plus 1u, but then du will be dx, and this will turn into u plus 1. I don't want that. So what I'm going to do is I'm going to call the other term, x plus 2, my u. Why? You see, the problem with integrating this is, okay, let me ask this. Why can't I integrate it without doing any substitution? Because I don't know how to integrate square root of x plus 2. I know how to integrate square root of x because it's of the form x to the power p. So what I'm thinking is, why don't I try to do some substitution so that I get rid of square root of x plus 2, but instead I get square root of whatever variable I'm going to have. So I am going to call x plus 2 my u. Then, when you take the derivative of the left-hand side, you're going to get 1. So 1 times dx is my du. So you will have oops. No, not that. This is supposed to be white. Yeah, you will have a square root u times the u here. What are you going to have, like, what are you going to do about this x plus 1? I need to write this in terms of u, because over here I want to have a function of u to integrate. So what I'm going to do is, well, I'm asking myself, what is x plus 1 in terms of u? Well, it's u minus 1, okay? And that's it. So I get this now. Now, this is the important part. You have to be careful. If you just write 0 and 3 here, and if this were an exam, I would just take off points for this. Because when you write this, that says something wrong. When I look at this definite integral, what I see is I'm supposed to integrate the function of u, which is u minus 1 squared u, over the interval 0, 3, where the variable, the numbers in this interval will be for the variable u. I'm like, when I look at this definite integral, I see that, oh, my variable is u. This is from u equals 0 to u equals 3. This is not the case. I made a substitution, okay? The original interval was for x, but I did a substitution, now I'm working with u. So I need to change these accordingly. When you plug in 0 for x, you're going to get 2 here. So this will be my lower limit. And when you plug in 3 for x, you're going to get 5. And this will be 5, okay? And now, okay. So this is for, I'm sorry, I want to, let's color this. Okay, now I want to integrate this function of u, and this is easy to integrate. Why? If you distribute this, this is what you will get, okay? And then this is u to the power 3 halves minus u to the power 1, and I know how to integrate this. This is u to the power of 5 halves divided by 5 halves, because the integral of the antiderivative of x to the power p is x to the power p plus 1 divided by p plus 1. So you add 1 to this and divide by that, and you get u squared divided by 2. And you are supposed to evaluate this from 2 to 5. So you're going to get whatever you're going to get. A 2 over 5 to the power of 5 halves minus 25 over 2 minus, I'm going to plug in 2 over 5. This is going to give me power 5 halves minus 2. Okay, so this is my definite integral, and that's it. So substitution with definite integrals work just like a substitution with indefinite integrals, except you have to keep changing the upper and lower limits of the integral. Okay, because if I wrote 3 and 0 here at these bounds, the result of that definite integral would be something else. Okay, it would be something which is longer. Okay, so we did that. Let me solve another example. So in this one, in this example, we're going to integrate a 2 to the power root x divided by root x from, let's go from 1 to 7. Okay. Now, I'm going to apply substitution method again to get this definite integral. A 2 to the power root x divided by root x. And then good. I'll have this. Now, what am I going to call which function will be called u? I can try to call a square root of x u, and that will work. I can also do something else. I can call the whole thing a 2 to the power root x u. What will happen then? So let me try that. Then let's take the derivative of the left hand side. Derivative of a to the power root x is, by chain rule, derivative of derivative of to the power x is to the power x times ln2. So I have ln2 times 2 to the power root x, and by chain rule I need to multiply this with a derivative of inside, which is root x, so its derivative is 1 over 2 root x. So I get that this is I get this equality. So I'm going to replace. Okay, I need to move this because I'm going to work with my boundaries in a second. So this expression 2 to the power root x divided by root x dx, it is equal to 2 over ln2 du. Okay, because if you put this ln u to the other side, like if you just divide all sides by ln2 and multiply all sides by 2, you're going to get that 2 to the power root x divided by root x dx is 2 du divided by ln2. So that's that. Now I need to change my upper and lower limits. Here's the thing. Some people don't like to change these upper and lower limits all the time, because sometimes while integrating you need to apply substitution rule like a couple times. Then like you will have to change the upper and lower limits a couple times, and some people don't like to do that. Instead, what they do is like sometimes people use the following notation. Okay, they say that I applied the substitution, but I'm not going to change these upper and lower limits because they're saying that eventually I'm going to go back to x. You'll see what I'm going to do in a second. And they will write these upper and lower limits as 1 and 7, but in order to specify that those limits are for x, they write x equals 1 and x equals 7. So this is a notation that people use. Now, why is this useful? Like, why am I doing this? Okay, let's integrate this. What's the integral of 1 with respect to u? It is simply u. Okay, so this is simply the integral of 1 is u. So integral of 2 over ln2 times 1 is 2 over ln2 times u. Okay, and I need to evaluate this from x equals 1 to x equals 7. Like this is, that's it. This is an antiderivative for this function. But here's the thing. How am I going to do this? Like, this is a function of u. This is like my evaluation symbol has x variables in it. So what am I going to do? I am going to first write everything in terms of x. So instead of u, I'm going to write 2 to the power root x, and then everything works out nicely. So I need to evaluate this function of x at these 2 points, and then I need to subtract these. Okay, and that's it. So remember, in while computing like while doing these examples, like, we did these substitutions, and at the end we changed everything back to x. Like, we didn't leave any terms involving u. What you can do while doing substitutions for definite integrals is you can just do that. You can do your substitutions and then go back to working with x. Okay, if you're planning to do that, then you don't need to change your upper and lower limits all the time. You can just keep them, but you should also write that like those are upper and lower limits for x. So you should just specify this. You should just write x equals blah blah, x equals blah blah. You can just keep them by writing these, and then go back to, like, after you find your antiderivative, you can just go back to working with x, and then you can evaluate your integral like this. Okay, so this is another thing that people do. Okay, that's that. So we solved this one as well. Now, let me talk about some trigonometric integrals. Okay. Some trigonometric integrals. Okay, do I want to solve more questions? Well, I mean, in your recitation video, which hopefully will appear in 2 weeks from when I upload this video, you will solve more questions, so I'm leaving that part to your recitation instructor. Yeah, let's start talking about trigonometric integrals. Now, I'm gonna find some trigonometric integrals. What I mean by trigonometric integrals? What people call trigonometric integrals is integrals where in the integrand you just see trigonometric functions. They are sums, maybe products, and so on. So I'm just gonna solve some example trigonometric, I'm just gonna find some example trigonometric integrals. Okay, let's find the integral of sine to the power 7x and cosine to the power 5x, and let's integrate this from 0 to pi. Okay, so the question is, find this. Now, when you see a trigonometric integral where you have a power of cosine and where you have a power of cosine times you have a power of sine, there is an algorithm which tells you how to compute that. Okay, so if your integrand is of this form, sine to the power something times cosine to the power something, there is an algorithm, and I'm going to solve 2 questions where I show you 2 cases that appear in that algorithm. What you do is, first you ask yourself the following question: is any of the powers that I see, the power of sine or power of cosine, like, are these powers odd or even? Is it the case that one of them is odd? If one of the powers is odd, then you're very lucky. There's a very easy method. In this case, it's both powers are odd, so I can do 2 substitutions, but I'm going to tell you what to do if one of the powers is odd. If you see an odd power, then let's say that that power is a that odd power is a it's the power of cosine. Then you split one over one of the cosines. Okay. If that odd power is a power, it's the power of sine, then you split one of the sines. Why are you doing this? Because you see, I'm going to do it in both ways. So let me do it like this. I'm going to do it in both ways. Yeah. Let me first split a power of cosine over here. If you do that, what's going to happen is, if in the next stage you call sine of x u, so I split a cosine, and if I call my sine of x u, then cosine of x dx will be my du, okay? So this is the reason I split the cosine. The expression cosine of x dx will become my du, and a instead of sine I can just write u, so I have u to the power 7 times instead of cosine x dx I'm going to write du. Now what's going to happen to cosine to the power 4? You see, if the power of cosine is odd and you split one of these cosines, then the remaining power of cosine will be even. In which case, you can write it as 1 minus sine squared to the power something. In this case, I'm going to write my cosine to the power 4 as 1 minus sine squared squared, because this is, not that. This is equal to cosine squared squared, which is equal to 1 minus sine squared squared, okay? So this, I should write this properly. This expression is equal to, this function is equal to 1 minus sine squared squared. And then, if you do that, you will get a polynomial, okay? And then, I'm going to change these boundaries, okay? Because in this case you get 0 and 0, so the integral will be 0. I don't want that to happen, so let's change this to 0 over 2. Yes. What was I saying? Oh, when you do the substitution, you will get a polynomial here, okay? Now let me change my boundaries as well. When I plug in a x equals 0, I get 0 over here. When I plug in x equals pi over 2, I get 1 over here. So I get a polynomial here, which you can easily, whose integral you can easily compute. This is like a u to the power 7 times 1 plus u to a 1 plus 1 minus 2 u squared plus u to the power 40 u, and then this is u to the power a. Let's distribute this. U to the power 7 minus 2 u to the power 9 minus, sorry, plus u to the power 11 du, and then the integral of this is u to the power 8 divided by 8 minus 2 u to the power 10 divided by 10 plus a u to the power 12 divided by 12, and you're supposed to evaluate this from 1 to 0. When you plug in 0, everything will be 0. When you plug in 1, you're going to get 1 over 8 minus 2 over 10 plus 1 over 12, okay? So this is the result. So what did I do? My integrand is of the form sine to the some power times cosine to the some power. I ask myself the following question: is one of the exponents odd? Yes. For example, the exponent of cosine is odd. So in that case, split one of the cosines and then call sine of xu, and then you're going to get a polynomial, which you know how to integrate because you know the integral of x to the power n. Okay. But then you can object to this and you can say that, well, the power of sine is also odd, so why don't I use that? You can. Indeed, let me do another solution written here. So in the second solution, because I see that the power of sine is also odd, I see that I can also like split one of the signs and do the exact same trick. So I'm gonna write this as sine to the power 6 times cosine to the power 5 a times sine of x dx, and I integrate this from 0 to pi over 2. Okay, so I split one of the signs here, and then I use the substitution cosine of x equals u, and then minus sine x dx will be my du. Okay, and then this integral will turn into, so instead of a sine to the power 6, I'm gonna write 1 minus u squared cubed. Okay, because this is equal to 1 minus cosine squared cubed, and then uh, and then instead of cosine, I'm going to write u. And instead of sine of x dx, I'm going to write minus du. So I have minus 1 times du. And as for my bounds, if you plug in 0 for x, you're going to get that u is 1. And if you plug in pi over 2, you're going to get that u is, if x is pi over 2, then u is 0. And now compute this definite integral, okay? So exercise. So it's going to give you the same result. So the point is, if you have an integrand of the form sine to the some power times cosine to the some power, like if your integrand of the form sine to some power times cosine to some power, then if one of the powers is odd, split one of those terms, call the other thing u. Okay? What are you going to do if both powers are even? Okay. Example. What are you going to do if both powers are even? In that case, you have to use the half angle formulas, and if you're lucky, those will turn your trigonometric integral into another trigonometric integral of the same form where the powers are now odd, okay? Or you keep successfully applying that. So let me show you. Let's find the integral of fourth power of cosine, okay? Now, this integrals of the form sine to some power times cosine to some power. Well, what's the power of sine? It's 0. This is sine to the power 0 times cosine to the power 4. Well, unfortunately, both of my powers in this case, both of the exponents are even. So what am I going to do then? Then you're going to use these half angle formulas, which tells you that, which ones? Yes. Now, if you remember the half angle formula for cosine 2x, this is equal to cosine squared x minus sine squared x. And if you replace sine squared minus 1 minus cosine squared, this is going to give you 2 cosine squared minus x minus 1. And this is the same, also the same thing as 1 minus 2 sine squared x. Okay? So this tells you that a cosine squared x is equal to 1 plus cosine 2x divided by 2, and sine squared x is a 1 minus cosine 2x divided by 2. Okay? Now, if both of your exponents are even and integral of the form sine to some power, cosine to some power, then you try to use these identities. For example, over here, what I'm going to do is, instead of cosine to the power 4, I'm going to write cosine squared to the power 2. And instead of cosine squared, I am going to write a 1 plus cosine 2x divided by 2. Okay? And then this will give me 1 over a 1 plus 2 cosine 2x plus cosine squared 2x divided by 4. And now I'm going to split this indefinite integral, just like, well, differentiation is linear, right? A derivative of a sum is sum of the derivatives, and you can pull constants in and out. So the same goes for anti-differentiation, which means that I can also, the indefinite integral is also linear, which means that the indefinite integral of a sum is sum of the indefinite integrals. You can pull the constants in and out, and so on. So this is the indefinite integral of 1 over 4 plus indefinite integral of 1/2 cosine 2x plus indefinite integral of cosine squared 2x divided by 4. And this one is easy to find. This is a x over 4, and this one is with some, like, with a, you have to apply substitution rule here, but if you call 2x your u, you can easily get that this is a sine 2x divided by 4. Okay, so take the derivative of this, you'll see that you get that. Maybe I should just write that down. Use a 2x equals u, and that you will get this. And then you get that over here, I'm going to use a substitution. I'm going to use the same substitution. 2x equals u. Maybe I should just write it down. 2x equals u. So 2 dx is du. And then this will turn into, now my dx is 1/2 du. So I have cosine squared u divided by 4 here. And then I'm going to use the exact same trick. I see an even power of cosine, so I am, instead of a cosine square u, I'm going to write 1 plus cosine 2u divided by 2. And then this will give you, okay, this is actually getting very long. So this will give you the integral of 1/2 is, with respect to u, is u over 2, and the integral of a cosine 2u divided by 2 is sine 2u divided by 4, okay, plus c. But I can't leave my answer like this because there's a u in it, but u is some variable that I introduced. So I'm just going to return, I'm just going to try to write everything in terms of x. So plus 1 over 8. So my u is 2x. So it's going to give me x here, and sine of 4x divided by 4, and I have plus c. Okay, so this is the integral of, this is the indefinite integral of cosine to the power of 4. Okay, so that's that. Let me solve another question like this, where both powers of sine and cosine are even. Okay. This was an indefinite integral, so let's make this definite. From 0 to pi over 3. Okay, let's find this definite integral. So what I'm going to do is I'm going to try to use those half angle identities that I mentioned. So instead of By the way, there's an easier way to get this integral by using the fact that sine 2x is 2 sine x cosine x, but let's not do that. I'm gonna do it directly using these identities. Now, what I'm gonna do is I'm gonna replace sine squared by 1 minus cosine 2x divided by 2, just like I had over here. And I have square root of this. And then instead of cosine squared, I'm gonna write 1 plus cosine 2x divided by 2. Okay? And then okay, this will get ugly, but I can't do much, right? So I'm gonna do it. 1 minus 2. If you square the numerator, you're gonna get a 1 minus 2 cosine 2x plus cosine squared 2x divided by 4 times 1 plus cosine 2x divided by 2. Okay, now I'm not going to finish solving this. I'm going to show you what will happen if I expand this. So multiply these out, you're going to get in one of parentheses, let's multiply these out. Oops. So let's multiply these out. I'm going to get a 1 plus cosine 2x minus 2 cosine 2x minus 2 cosine squared 2x, a plus cosine squared 2x plus cosine cube 2x dx. Okay, and then some things will cancel each other, so you're going to get minus cosine 2x here, and then you're going to get minus cosine squared 2x here. So this will be 1 minus cosine 2x, a minus cosine squared 2x plus cosine cube 2x, and then that's that. Now let me do a very simple substitution. U equals 2x and the u will be 2dx. So you will get here. So if you plug in 0 for x, you're going to get u is 0. If you plug in pi over 2, you're going to get that u is 2 pi over. If you plug in pi over 3, you're going to get that u is 2 pi over 3. So you are going to get that 1 over 8, 1 minus cosine u minus cosine squared u plus cosine cubed u. And then the rest is exercise. The rest is easy because why? You know how to integrate cosine, that's fine. You know how to integrate cosine to some even power, use the exact same trick. And this is an odd power of cosine. Like I can think of this as sine to some even power times cosine to some odd power. When you see an odd power of cosine, what do? You split one of those cosines and do the exact same trick. So you can easily get this integral. So now you know what to do if you see an integrand of the form sine to some power times cosine to some power. If one of the powers is odd, it's easy. If both of them are even, then you use these half angle identities for cosine to get something simpler. Like you may have to use these half angle identities over and over again, but eventually everything will boil down to either a second power of sine and cosine or some odd power of sine and cosine, which you know how to integrate. So you can actually write down a computer program which just finds these indefinite integrals by doing these. Okay, it's like if one of the powers is odd, split one. If both of them are even, apply the half angle identities for cosine. Well, when I say half angle identities for cosine, I mean these. Like write cosine squared and sine squared in terms of cosine 2x, and then expand your integrand. You will get some other trig, a trigonometric integral, and keep doing the exact same thing, and eventually either you will get an odd power of sine or cosine, or you will get the second power of sine and cosine, and you know how to integrate these. Okay, so that's that. And finally, let me talk about trigonometric integrals of the form secant times tangent. We may ask, like, you may ask yourself, like, why are we dealing with these special trigonometric integrals? I mean, there are like infinitely many different ways of combining these. Why are we sticking to these? Well, honestly, just because your book does that. Okay, I mean, in this substitution section, because these trigonometric integrals are nice examples to illustrate substitutions. Like, you see what's going on over here, and you see what happened over here. These are like nice examples where you can illustrate the substitution method. So this is why we're solving these. Okay. Anyway, let's find the indefinite integral of secant power 3 tangent to the power 5. Now, if you see a trigonometric integral of the form secant to some power times tangent to some power, then it is very likely that the substitution method will help you. Why? Because derivative of tangent is secant squared, and derivative of secant is secant tangent. So if I call one of these terms secant or tangent u, then I will see du in my integrand, because like if I call tangent of xu, then secant squared x dx will be my du, and if I call secant xu, then secant x dx will be my du. Okay, and then using some trigonometric identities that relates tangent squared and secant squared, namely the identity that 1 plus tangent squared is secant squared, will allow you to simplify things. So let me show you what I mean by on this specific example. Okay. So over here, I am going to call my secant x a u. Okay. So I'm going to call my secant of x u. If I call my secant of x u, what's going to happen? Then secant of x tangent of x, which is the derivative of secant. So secant of x tangent of x dx will be my du. Okay. So I'm going to have the following. Maybe I should do the substitution later. Let me do it over here. So I'm going to separate one secant. I'm going to split one secant from this and one tangent from this. And I'm going to write secant x tangent x dx over here. And when I do the substitution now, this will give me, you see, this whole expression will be my du. So I need to express these in terms of u, but that's actually easy, because I am also going to use the following fact. 1 plus tangent squared x is secant squared x. Okay, so I get that tangent squared x is secant squared minus 1, which is u squared minus 1. Okay, so I have that as well. So tangent squared is u squared minus 1, and secant is u. So I'm going to have a u squared times u squared minus 1 squared du here, and this is polynomial. Now you know how to integrate polynomials, so this is an exercise. Okay,